The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, good evening, good morning, wherever you are in different parts of the world. Good to see you all. Good to have you join us. They're exciting, really exciting presentation for you today. It's about Geospace Storms. Wow, and I've seen some of these slides that he has, and they're really beautiful. Mysteries of Geospace Storms. And this is from Dr. Slava Merkin at Johns Hopkins University. And you might have already seen the abstract that was sent out to you. And Dr. Merkin has 20 years of experience in numerical modeling of space plasmas, in particular simulation of the Earth's magnetosphere and the inner heliosphere. His work on development of plasma space simulation codes and coupling between different physical regions and regimes has spanned the domains from Earth's ionosphere to magnetosphere and solar wind, contributed to many areas of space plasma research, including the physics of strongly driven magnetosphere, magnetopause boundary instabilities, particle acceleration, etc. Since March 2020, he's been the principal investigator of the NASA DRIV Science Center for Geospace Storms. So exciting times. So let's look forward to your presentation, Dr. Merkin, and I'm going to make you a presenter in just a second. And here we go. Just click show my screen and you're ready to go.
Okay, I hope you can all see my screen.
Yeah. Perfect.
So thank you very much for being here. I'm very excited to talk to you about this topic, about the science that we do and how beautiful it is out there in geospace. From this title slide, you can probably imagine I'm going to talk about something that has to do with the aurora. But it all actually starts at the sun, what we do. And so before we start talking about geospace, let me talk to you about space weather and what it is. So space weather, as the slide says, starts on the sun. You know, it's our beautiful star. It is always active, and in particular during periods that we call solar maxima. You know, there is the solar cycle, which runs about 11 years between solar minimum and solar maximum. During solar maximum, our sun develops these very beautiful active regions which erupt and create these big clouds of mass that propagate through the interplanetary medium and impact the Earth. And collectively, all of those interactions are called space weather. So I'm going to talk to you about that. This is, of course, an image of the Parker Solar Probe, which is one of the many NASA missions that are out there in space studying the sun and the geospace system and space weather in general. I don't know if you've noticed, but there's this little dot here on the slide, and that's us, that's our planet. Not many people realize this, but the Earth is much, much smaller than the sun. It's about 100 times smaller than the sun. And so I tried to put this image of the Earth here actually to scale. So it is really tiny compared to the sun. And when active regions like this erupt, they create disturbances that really dwarf our planet and the surrounding near Earth space. So what happens when the sun erupts? These are beautiful videos from the NASA missions, Solar Dynamics Explorer and Stereo here. you know, there are plenty of these movies on the web, by the way. You can find them and look at them yourselves. You can see here a close-up view of an eruption on the sun, which creates this bubble of gas, or we call it plasma, which is ionized gas, that erupts over the sun and propagates toward the Earth. And here you can see a zoomed out view, also from a NASA mission, of these bubbles right here, erupting and propagating. And we call these things coronal mass ejections. And this is pretty much the first thing that happens when you study space weather. So since I'm talking to a fairly technical audience, I thought I would kind of intermix a few more technical slides just to give you guys a flavor of what we do in our everyday work. So to put things into perspective, the image on the upper left here is again from the NASA Stereo spacecraft. It's sort of looking sideways at the coronal mass ejection here. I hope you can see my mouse. And this disk here is has the radius of 5 solar radii. I'm telling you about the sizes of these things, again, just to emphasize how tiny the Earth, us, are. Once this bubble of mass or coronal mass ejection leaves the solar corona here I'm picking it up, so to speak, in a simulation, in a computer simulation that we do. This is actually from the work that my close colleague is doing. And so here you see this bubble and the corresponding magnetic field. You can see this tangled magnetic structure here that accompanies the plasma bubble, leaving a region here. This ball has the radius of 20 solar radii. So again, to put things into perspective, the distance from here, from the center to out here, is about 200 solar radii. So at this scale, us, the planet, is about 20,000 times smaller than the size of this distance here. So it would be a dot. You wouldn't see this even here on this plot. When this bubble, this tangled magnetic field structure propagates further out, it becomes bigger, it expands. And so here in the bottom row, you can see another simulation from a different group that looks from top down on a coronal mass ejection. And you can see that sometimes this was a particularly big. It even propagates in all directions from the sun, as you can see here. But the main point that I want you to take away from this is that us, the planet, would be really, really tiny here. So these big things, these coronal mass ejections, these plasma bubbles and tangled magnetic fields, they erupt from the sun, propagate through the interplanetary medium, and blow past us without even noticing. And yet at the same time, they, as one of the science writers working with us said, they wreak havoc in the near-Earth environment. They do that without even noticing us. That's the irony of space weather. So just to give you another view from another simulation that we did, again, us would be here. This is tiny. This is the ecliptic plane. So the Earth would be circling around Sun, around the boundary of this plane here. This ball here is 20 solar radii, and you can see how this coronal mass ejection and the magnetic field that is associated with it propagates through the interplanetary medium and ultimately reaches Earth. So what happens when these magnetic fields and this plasma start interacting with the near-Earth space? And that's where we enter that's where we enter geospace. So let me tell you about this image here. So this is obviously the Earth here. The sun is to the left, and the solar wind and the coronal mass ejections, they blow from left to right here. The Earth system is dominated by the Earth's dipole magnetic field. You can see these field lines depicted here. What happens when this system interacts with the these clouds of mass and magnetic field propagating from the sun is that the Earth's dipole field is compressed here on the day side and stretched out on the night side. But altogether, the magnetic field of the Earth creates this protective balloon or cocoon, sometimes people say, around the Earth, which protects us from the hazardous effects of the solar disturbances. But this interaction does create a pathway for energy input from the these coronal mass ejections into the Earth system, and this is when space weather happens. So before we get there, let me play you a movie that this picture is based on, and then I'll tell you a little bit about this movie. So here you can see this is the sun. These are the orbits of planets. It's a little bit distorted because it was actually made for a planetarium dome. So I'll tell you a little bit about that planetarium show. But right here is the Earth, and that's the moon around the Earth. And you will see, as we get closer to the Earth, you'll see the image of the magnetosphere appearing. And this movie here is actually based on an actual computer simulation that we did in my group. So it's an actual simulation of a geospace storm when the Earth system interacts with a coronal mass ejection that will impact it. As we zoom in on the Earth system, you will see here, this is something that they called in the planetarium show the Technosphere. So let me stop it here. These are all actual satellites that are circling the Earth. These are not made up. These are actual spacecraft, actual satellites that are out there. This right here is the geosynchronous orbit where we have a lot of communication satellites. And you have a lot of other satellites as you're getting closer. There's a lot of satellites here in the low Earth orbit. And so collectively, all of this technology, all of this infrastructure, you could call it the Technosphere. And this is, the Technosphere is what is most affected by space weather effects. So let me tell you a little bit about this movie. We actually worked with the Hayden Planetarium and the American Museum of Natural History on this movie, on this movie and on this planetarium show. And it would have been playing right now in the museum if not for the global pandemic. But maybe at some point you'll be able to visit New York and see this. Curiously enough, these colleagues of ours that worked on this planetarium show, they actually, with this sequence, were selected for the official selection in the SIGGRAPH conference, which I didn't know about, but to computer animation aficionados, this is a really, really big deal. So for those of you who are out there who know about this, apparently it is a big deal. So going back to this Technosphere. So let me tell you a little bit about the effects of space weather. Again, you can Google a lot of these images on the web. This one in particular is from the National Oceanic and Atmospheric Association in the US, which kind of summarizes all of the space weather effects that are out there. And there are a lot of them. They start with further out in space with all these satellites and spacecraft that we were just talking about, you know, the energetic charged particles, both electrons and protons, they affect the electronics within these space assets, and sometimes they can damage them or even take them out, which is bad for many reasons, obviously, and in particular for communication. But those are not the only space weather effects. As you get closer to the Earth, basically in the near Earth atmosphere, about 100 kilometers altitude or so, the atmosphere is ionized, and we use that ionized layer of the atmosphere for communications. And so when that layer of the atmosphere is disturbed by the solar disturbances, you can have significant effects on communication, and in particular GPS signal scintillation. Also, another important space weather effect is the effect of so-called geomagnetically induced currents. So basically, the currents that flow out in space, they affect the power grid and even pipelines that are underground, by inducing currents there. And so sometimes you can have power outages. There are some famous situations when a particularly big solar storm or geospace storm happened, when the entire province of Quebec in Canada, I think it was in in 89, that exhibited a blackout. So these are particularly big effects that don't happen very often, but almost in everyday life, smaller scale effects of space weather are observed in all of these industries that are affected. So I just told you about the sort of the applied side of space weather, but in fact, it's an incredibly complex scientific problem to deal with. And so let me talk to you a little bit about the science of space weather, so to speak. Oh yeah, I forgot that I included this slide. I wanted to say that prediction of space weather is today nowhere near where prediction of atmospheric weather is, where you can see a forecast on TV every day. But that's not to say that we haven't made a lot of progress. And in fact, you know, there are these facilities like the Space Weather Prediction Center in the US, which is operated by NOAA, where people do track these space weather disturbances and make predictions for the affected industries. So going from this now to a little bit the science of this system, let me tell you a little bit about it. So I started talking about geospace to you, but I never told you what geospace is. So let me define it. Geospace comprises the near-Earth environment that starts about at 70 kilometers altitude, so that's the upper atmosphere, and extends to the outer reaches of the magnetosphere. That's that protective cocoon that that is surrounding the Earth, that's formed by its magnetic field. And it can extend all the way to about 2 million kilometers. So we're talking about an incredibly large and multi-scale system. And this is the system that you see here. This is the magnetosphere that I told you about. The solar wind would be blowing from left to right here. This is the equatorial plane of the magnetosphere. You can see this is the magnetospheric boundary, and it sometimes has these wavy perturbations or instabilities. This is the magnetotail, as we call it, where some very high-speed flows, which are somewhat turbulent, shoot down toward the Earth and bring the energy and particles that they ultimately acquire from the solar wind. But as you zoom in on the Earth, the magnetosphere actually interacts with the ionosphere, which is the upper layer of the atmosphere and which is ionized. And then below that is the atmosphere, which is the neutral gas, which we're living in. However, if you zoom in on this region, if you're looking at it from the point of view of the global magnetosphere, it's really tiny. It's just a little thin shell surrounding the Earth. But if you zoom in, you will see that it's actually a large and complex system in and of itself. Here is a somewhat distorted image of the atmosphere extending from 100 to 400 kilometers here. And you can see that there's a lot of variability and structure inside. And so the interesting part about geospace is that it's not only driven by the solar wind, which is from above, but also is affected, or sometimes we say preconditioned, by the lower atmosphere. And so this geospace system is, if you want to study it, you need to study both its interaction with the solar wind and with the lower atmosphere. And that's why we started calling it the multi-scale atmosphere geospace environment, or MAGE. And this is what this guy is doing here. And I'll talk to you about this guy, in a second. So to understand the physics of geospace storms and predict space weather, we need to study the multi-scale atmosphere geospace environment. So how do we do that? How do we study this environment? Well, we build spacecraft. This is the image I took from the NASA website. It's called the Heliophysics System Observatory. And you can see here a lot of spacecraft that were built and are operated by NASA, but also by other space agencies, for example, the European Space Agency, or there's a Japanese spacecraft. And all in all, there are a lot of these assets that we operate out there in space, observing these disturbances all the way from the sun, tracking them through the interplanetary medium, and then within geospace. But building spacecraft is not the only thing that we do. We also build computer models. And this is what we do in the Center for Geospace Storms that I'm leading. And as you can see, what we want to do within this center is to ultimately transform the understanding and predictability of space weather. And we will do this by building a comprehensive model of geospace that I'll talk to you about in a second. This is, by the way, another image that graphics artists made, but this is based on an actual supercomputer simulation that we did. So I'm going to come back now to this image that I showed you and to this Gandalf-y figure here, because the MAGE is actually what we call this supercomputer model that we are building. The multi-scale atmosphere geospace environment model. And the image that you see here is actually composed from our simulations. These are all actual computer simulations that we visualized here. So again, to give you a little bit of a technical detail here, I'm not going to talk about all the details about these models, but I'm going to just mention that the physics of geospace is multi-scale. It occurs across a very broad range of scales. As I said, we need to resolve distances essentially from the ground all the way up to a couple million kilometers. But also the physics is heterogeneous. And what we mean by that is that the different systems within geospace are described by different physics, and you need to build different models to describe these regions. And so any comprehensive model of a storm time geospace is actually a framework of coupled regional models. So what you see here is a lot of different models that different groups work on that we make interface each other and sort of work with each other seamlessly. And not only do you need to couple them, you need to make them all together as a coupled framework run on modern software architectures and even anticipate future advances in supercomputer technology, which is changing constantly. So what I thought I would do here, again, because I'm talking a little bit because I'm talking to a fairly technical audience, I'll give you a couple of examples of our simulations just to give you a flavor of what it looks like and what it entails. So I'll show you two examples. One is from the model of the global magnetosphere, the model that we call GEMARA, which stands for Grid Agnostic MHD for extended research applications. MHD is magnetohydrodynamics, so it's just like hydrodynamics, but with magnetic fields embedded in it. And what you can see here in this movie is the magnetosphere looking down on the equatorial plane, and this is in the meridional plane. And this here are actually projections of the polar caps looking down from the northern pole and from the southern pole. This is just to give you an idea of how incredibly dynamic and turbulent this system is. There are these boundary instabilities. There's this turbulence that you will see in a little while. Here a space storm starts, and you can see how these flows propagate from the magnetotail, as we call it, toward the Earth. They are very dynamic and very bursty, as we say. And so the way we simulate this system is by solving numerically the equations of magnetohydrodynamics using some very precise numerical techniques and some pretty cool algorithms that, for example, work on distorted grids like this one. So if you're out there doing some sort of numerical simulations, this might be of interest to you. Just to give you an idea of, this is not just pretty pictures. This is actually giving us some idea of what happens in reality. Recently with this simulation, we did this work, which got a lot of coverage in press. This is where we looked at these so-called auroral beads. You can see here the Earth's aurora seen from the International Space Station, and you can see that the aurora has these local structures. They're about 100 kilometers in size. So from our point of view, from a global magnetosphere point simulation, these are very, very tiny. And what you see here on the right is our simulation looking down on the equatorial plane of the magnetosphere. You will see here, hopefully the screen gives it, doesn't prohibit you from viewing this. There are little things that look like drops in the lava lamp or something. And they, when you map them to the ionosphere, they create these little beads that you can see sometimes here. And this is what creates, we've shown, this is what creates these beads in the aurora. And we can even compare those that we simulate with those that are observed, and they line up pretty nicely, even though you can see that nature has, unfortunately or fortunately, very high resolution. So even with super high resolution simulations that we ran on something like 10,000 computer cores on a supercomputer, even with that, all of that computing power, we are still barely resolving the structures. And so this is where we were able to resolve structures between 30 kilometers all the way to 2 million kilometers within the same simulation model. Give you another example of computer simulations that we do. This is now going below to the atmosphere. And this is a very cool simulation that coupled two models. One of the models here is the atmospheric model from my colleagues at National Center for Atmospheric Research. You can see here, this is the globe, and you can see here a global pattern of the atmospheric winds simulated. This is not reality, this is simulated reality, so to speak. You can see how incredibly well resolved this pattern is, and these are winds at about 100 kilometers altitude. What's interesting is that if I kind of slice it with a plane that's perpendicular to this go out of the plane of the screen, you can look here. This would be looking up this axis here, so the ground would be here. And here in this thin layer in the lower atmosphere, we have these waves that you see here. But if you go further up in altitude to about 300 kilometers or more, you see these bubbles propagating upward. And these bubbles in the ionosphere are very interesting from the space weather point of view because they create problems for communication. So what's interesting is that in this simulation where my colleagues coupled the atmospheric model to a model of the ionosphere that kind of covers this region at higher altitudes, they were able to see these bubbles with these very small scale atmospheric waves. And so what you see here is this pattern of bubbles sort of looking down from space on a globe in the model. And this is from an actual NASA mission GOLD observations. You can see how incredibly similar they are. So this is another example where coupling models that cover different regions of geospace at very high resolution results in these very realistically looking simulations that actually make space weather predictions. So I'm gonna start wrapping up here, and we'll sort of circle back to the where I started, which is the mysteries of Geospace Storms. So I'm not going to make you understand everything in these images. In fact, these images are sort of textbook pictures that are much overused in various talks that we give. The one on the left is an image, a textbook image of the magnetosphere with, as you can see here, with the various regions of the magnetosphere that are coupled with each other and interact one way or another. And then down below here, if you zoom in, you see the ionosphere, thermosphere, which is the upper layer of the atmosphere, and the atmosphere, all coupled together with incredible complexity. And another important point is that the range of altitudes, just to reiterate, we're talking here about a very complex system that spans, from the ground to 1,000 kilometers. But then, as you go from here to the magnetosphere, you extend it all the way to 2 million kilometers. And so, what's interesting about this is that we've studied this system for years and decades, and we know a lot about all of these interactions that happen inside these different regional systems. But we surprisingly know very little about how all parts of geospace work collectively. And this is particularly important during storm time because it's during storms when the system is excited by the strong solar disturbances. All of these parts of geospace start working collectively. And this collective behavior shapes the response of geospace to solar disturbances. But we know, in fact, quite little about how the system behaves collectively. And another important point is that all of these collective interactions, as I said, they operate across a very wide range of scales. And so just how exactly these collective interactions occur across a wide range of scales, we don't really know. And this is what we're trying to study with all of those missions that I mentioned, and also with the computer models, such as the one that we're building within the Center for Geospace Storms. So just to reiterate, the challenges of predicting space weather are, they abound. They start from all the way from the sun, they propagate through the interplanetary medium, and then they impact geospace. And the response of geospace involves multitude of charge and neutral particle populations or gases that coexist in the magnetosphere, in the ionosphere here with its beautiful aurora, and with the atmosphere. And they coexist and interact strongly with each other and with the electromagnetic fields across various scales and domains. And so if we're building a computer model that wants to simulate this system, preferably it should include all of these interactions within itself. And this is an incredibly complex problem, and so is predicting space weather. So I'm going to go to my last slide and kind of conclude with this question. What does it take to predict space weather? And there are sort of three components to this. One is, as I just described, and hopefully convinced you, you need to address a grand science challenge. Storm time geospace is a system of systems that manifests some of the most complex and least understood multi-scale interactions in space and solar physics. Understanding this system, particularly during strong disturbances, requires describing it in its entirety while resolving a broad range of scales. And as I just said on the previous slide, that is an incredibly complex problem, and so is predicting space weather. And so, therefore, it takes a village. You cannot do it within a one group or two groups. It takes the entire scientific community, and the way we do this is, you need to empower the community. We empower the community by building space missions and various ground facilities for tracking these disturbances and for studying geospace, their geospace effects, and also by developing open source whole geospaces, we call them multi-physics simulation models for community use. And finally, which is last but not the least, is educating your workforce. We need to ensure training a new and diverse generation of scientists that will integrate knowledge across different domains, different space science disciplines and approaches, which include theory, modeling, data analysis, and computer science. And so if you're a young graduate student or a scientist out there, feel free to reach out to us. I give a feedback link here. We're happy to hear from you. And I'm going to stop here and see if there are any questions.
Wow, that was, Slava, that was mind-blowing, literally. So much interesting stuff happening out there that we're not aware of, and that you have given us a little window to peek at what's happening out there in space. Fantastic. Opportunity for all of you who are here. We got some good friends in the audience, and I'm sure there'll be some good questions coming up, okay? Let's take them as you come along. So don't feel shy, just jump in. We are all in the same boat here. We don't know too much about what the details of what Slava talked about, but I think it's fascinating stuff. There's Sanjay is asking, what's the closest distance a probe can approach the sun before burning up?
Oh, that's a very interesting question. Let me go back to the beginning. I'm afraid I might not be able to give you a distance in kilometers, but the Parker Solar Probe is the first ever human object that made it this close, and I think it was something like, I don't want to make a mistake, I think it was 0.1 astronomical unit, which is about 20 solar radii or so, which is, one solar radius is 700,000 kilometers. So you do the math.
That's a lot. That's pretty good, actually, to get that close. Question
from
Sam.
This is, I was just going to say, this spacecraft is an engineering genius because it has this shield in front of it, which has an incredible gradient in temperature across it. It protects the spacecraft from the radiation. It's amazing.
I would think the limiting factor would be the temperature, right? Because we don't have materials that can go that high. Would that be the limiting technology in terms of getting close to the sun?
Oh yeah, this is, I'm the wrong person to talk about this, but like I said, it's an engineering genius, this spacecraft, and you can go to the web page and look at how they, what materials they used, and it's fascinating.
So this is next one from Samuel Mukasa. Do corona mass ejections happen more or less in the same location on the sun, which would make forecasting of the impact on Earth much easier?
No, they occur all over the place pretty much, and particularly during solar maxima, they kind of pop out anywhere. And one of the major problems is that we, in this entire space weather prediction enterprise, is that we cannot really today predict where exactly it will occur. And this is one of the biggest major problems.
A question from Felix. For building these models that you build, how do you decide the test data, and how do you train the data for developing this model?
Very good question. So it very much depends on the model, right? Because as I said, each domain of geospace, or for example of the solar corona or interplanetary medium, is treated by a different model, and so we take different data. The geospace models, if I go to the, I think this is it. If I go here, you can see here that there are spacecraft that are upstream, as we call them, the ACE spacecraft, the WIND spacecraft, that are just upstream of the magnetosphere, and they're sitting there pretty much all the time at the so-called L1 point, which is a stable orbit. So they just sit there and observe the solar wind all the time, and we use them to drive our simulations upstream. Now, there are a lot of data inside the magnetosphere, for example, that we can then, when we run our model, we can then compare with this data and validate. And this is an ongoing exercise. Hundreds of papers are written every year on these validation exercises. But there are a lot of data out there to both drive our models and validate them.
From another question from Sam Mukasa, does space weather create lightning, for example, in the bubbles?
No, lightnings occur much closer to the Earth, but they create waves actually that propagate into the outer space. So you can actually see effects of lightning out there. But lightning is caused by lower atmospheric processes.
Question from Anil Pandit here. Will the corona mass discharge also affect the shadowed side of the Earth? Will it last till the shadowed side comes facing it on the rotation?
So if I understood the question correctly, will a coronal mass ejection affect the night side of the Earth? And yes, absolutely. This is one of the major regions of the magnetosphere where actually the solar wind energy is stored. So if I go back to this image here, you can see here that, as I was explaining, on the day side, the magnetosphere is compressed, as you can see here. On the night side, it's stretched. And particularly this dark region here, which looks like there is nothing, it looks like there's nothing only because what's plotted there is plasma pressure. If I plotted there the pressure or the energy of the magnetic field, you would see that this is, in this black region, is actually where most of the magnetic field energy is stored. And so when a solar disturbance or coronal mass ejection impacts the Earth, it's here in this vast black region, which is called the magnetotail lobes, is where that energy is stored. And it's an enormous amount of energy, which then, through a process that is not very well understood, through magnetic reconnection, that energy can enter the magnetosphere, and this is what creates these high-speed flows and turbulence.
A follow-up to that from Anil is, will the corona mass discharge be impact or alter during the solar eclipse? Will the corona mass discharge impact alter during the solar eclipse?
Oh yeah, this is, solar eclipses are actually one of the best times to observe the sun, because you can the brightest part of the sun is blocked out, so you can see the solar corona and its structure. So during solar eclipses, we're just the sun is hidden behind the moon, so to speak, but coronal mass ejections still occur.
So this is from Ami, but what kind of effect does geospace weather have on our own atmosphere closer to the Earth?
Oh, interesting question. So, like I said, there at higher altitudes, let's say 100 kilometers, 70 to 100 kilometers, there are very strong effects because that's where most of the energy of the solar storms is deposited, and so the entire we call it the thermosphere, the upper region of the atmosphere is basically all stirred up, and you create winds and so forth. One of the interesting effects that people are looking at a lot recently is the effect of very high energy particles that penetrate down to the lower atmosphere, and they actually change chemistry, for example, of the processes there. Some people I've heard even believe that it may have to do with climate, effects of highly energetic particles. And of course, the most spectacular effect in the atmosphere is actually the aurora that I start my slides with. This is where the energetic particles from the magnetosphere penetrate closer to the Earth to, dependent on the energy, to 80 or 100 kilometers. They excite molecules there that emit this light that we see as aurora.
Okay, next question from Madhu Atre. In your modeling, do you have to consider relativistic effects, or is the physics non-relativistic?
So a very, very good question. It depends very much on what part of geospace you're looking at, and this is why I said that it's multi-scale and the physics is multi-scale and heterogeneous. Closer to the Earth, around here, hopefully you can see my mouse, we have the radiation belts, and they are spanning, anywhere from 2-3 Earth radii to about geosynchronous orbit, which is about 6 Earth radii, and the Earth radius is 6,400 kilometers, give or take. So the radiation belts consist of electrons which are very high energy, and they are relativistic for sure. And so if you are studying radiation belts, yes, absolutely you need to use models that include relativistic effects. Out here in the outer magnetosphere, no, the flows are, for example, these plasma flows that you see here, their speed is, 1,000 kilometers per second would be a high-speed flow. But there's still, 1,000 kilometers per second is a very, very high speed, as you can imagine, but it's still not really relativistic.
So from Sampath Kumar, is there any significant difference in the model estimations by considering the revised sunspot numbers rather than the previous sunspot numbers for the thermosphere, ionosphere model in specific?
Yes, yes, absolutely. The sunspot number is one of the key parameters actually in all of this modeling. So the higher it is, the higher is the conductivity of the ionosphere. And the conductivity of the ionosphere is one of the most critical parameters, both for the ionosphere thermosphere physics and for the magnetospheric physics.
For the last question again from Sam Mukasa, it looks like the magnetosphere protects us from the nasty high velocity particles in the solar wind. How come life is not wiped out completely during magnetic reversals when Earth's dipole field goes to zero?
A very good question. I actually don't know. Have we lived through a dipole reversal as a humanity?
Okay, well, on that note, let us call it quits for today. And Hans Foy would like to say, Samuel says, yeah, the many times. Samuel Mukasa says that reversal happens many times. So I guess we'll let Hans Foy have the last word here. Come in, Hans.
Thank you very, very much. I want to take this opportunity to also thank Dr. Nelly Mosavi, a colleague of our distinguished speaker at Johns Hopkins University, a new leader there, who introduced me to Dr. Merkin, and this very, very fascinating presentation here. So thank you very much, not only to you, Dr. Merkin, but certainly to Dr. Nelly Mosavi. I do have a question, and then after that, just a couple of comments, because we have many members of our global IFEES GDC community. One question specifically in terms of the work that you do, Slava, is what collaboration do you have with what other countries and universities that are the most important given this complex field that you work in?
Yeah, so the collaborations that we have are mostly with countries that have either have historically space science programs. These include certainly Japan, Russia, China, countries in Europe because of the European Space Agency, the UK, Germany, France, Italy, all of our European partners. But for example, it's not what I do, but my colleagues who study the ionosphere, atmosphere, for example, the countries that are more toward the equator are much more affected by space weather in the ionosphere. And so I know that countries that basically to lower latitudes, the countries in the South America, in India, are very much involved in this research.
No, thank you very much. Again, I really want to thank you deeply for this presentation, but to all of our other members of our global community that I appreciate that joined us, I want to remind you and put on your busy schedules our global conference, virtual conference in November, bringing engineering students, faculty, deans, corporate colleagues together. And please write to me, to us, to give you further information. Also, this year we will continue to have a GDC Diversity Award, recognizing the creative work around diversity issues at a global level. I just wanted all of you to be aware. And finally, we're working very diligently with our friends at McMaster University and Petrus Communication in Paris for our, at the end of this month, our GDC Industry Forum. Very dynamic. I'm very happy. Any of you interested, just please write to me and join us. Krishna, thank you for facilitating this fascinating presentation.
Thank you so much.
Many thanks.
Yeah, fascinating presentation, Slava, and it has taken us literally into a different world out there.
Yes.
And so everybody, I hope I wish everybody happy, be healthy, be happy, and be safe. And take care. That's the end.
Bye-bye,
Thank you very
everybody.
much, everybody, for your attention. Bye-bye.
Thank you. Bye-bye. Peace be with you.
Bye-bye.
Bye-bye.